Okay, right. So it's my great pleasure to welcome Nate Foster. So just a few words about Nate. So he got his PhD at University of Pennsylvania under Benjamin Pierce. He was a postdoc after that at Princeton University, and now he's a professor at Cornell University, and just recently did a sabbatical at Barefoot Networks. So Nate is very well known for his contributions to programming languages and networking, and basically creating programming languages for building, creating more reliable networks. And I would say that his work really has triggered a lot of follow-up research, and inspired a lot of people to get into this area of programming language and networks. So I'm very happy and excited for his talk. So please go ahead.
If you go home to see your parents or maybe your grandparents, and the first thing they ask you to do is to help you fix their Wi-Fi. Do you ever have this experience? A few names. I actually had this experience with my wife. We were on I think our third date, and she had me over for dinner. And as I was leaving, she said, "Could you fix my Wi-Fi?" And I think there's something to this that networks tend to be kind of difficult to manage. And this is true of your grandparents in their house with their Wi-Fi. It's also true of people who do this professionally. So there are engineers called network operators whose job is basically keeping networks running. And they have a whole bunch of techniques that they use to do this, from having domain-specific kind of configuration languages that they design themselves, and then generating device configurations from those higher-level policies. They have all kinds of crazy tools that go and scrape the configurations off of routers and switches and so on, and then do some kind of analysis on them. And then they have command line tools like ping and traceroute, which I've shown here, which let them kind of dynamically probe the network and see what it's doing. And despite this, the networks have sort of proven to be very difficult to manage, especially as they scale up. So if you step back and sort of remember, how are networks today designed? What principles are they based on? You can go back and read classic papers like Clark's The Design Philosophy of the DARPA Internet Protocols, and look at some of the things that they were thinking about as they sort of laid down the structure of modern networks. And if I was to sort of say this in cartoon form, I would say that the main principle that the internet was designed around was robustness. So they were trying to build a network that could interoperate with many other networks. They wanted to have devices provided by many vendors. There were different conventions for what kinds of protocols you might use, what kinds of services the network might provide, what kinds of applications are running. And they wanted to build this network that would sort of serve all those needs. And so by robustness, I mean that the internet sort of works even when some devices misbehave or fail. For the most part, you're still able to communicate sort of around the world, and that's amazing. But this design actually defers a lot of important issues like performance, security, accountability, and so on. And so maybe about 10 or so years ago, networks really became central to modern computing systems. You see things like the rise of data centers, which power all the cloud computing and sort of modern web services. And the networks in those data centers really play a critical role for allowing them to scale up, and also allowing all of our PCs and phones and so on to communicate with all the machines in those data centers. And so this is a picture of actually Facebook's data center design, and a picture of inside their data center. And you see that these networks are getting really large and really complex. And so the tools that network operators have been using to manage them have not really been up to the task. And so people have started to think about how they might start to take ideas from the software domain, and in particular formal verification techniques, and start to apply them to networks. And the kind of properties that you might care about in a network, you might kind of classify a lot of these as sort of reachability properties. Can packets that of a particular type that are in this place in the network, will the network forward them somewhere else? Can these packets reach somewhere else? And so you can look at things like, connectivity. Does the network actually connect all the hosts that are connected to it? Fault tolerance. If a node or a link goes down, is there still a path, and will the network basically provide that path to traffic between two endpoints? Isolation. If you're talking about, say, a cloud network where you have multiple tenants that are sharing that cloud, you may want to make sure that their traffic can actually interfere with each other. And so you'd like, actually, the opposite of connectivity. You'd like it to be impossible for some other tenant on a shared cloud to be able to snoop on or interfere with your traffic. There's other kinds of reachability properties like loop freedom and black hole freedom. So loop freedom simply means that there's no path through the network where packets of a particular type can get back to exactly the same place with the same value, because of course that means that the packet will spin around forever. And a similar property is black hole freedom. You'd like to know that if a packet is going to be dropped somewhere, then it's not dropped deep down inside the network, but it's dropped at or close to the edge. Then there's other properties like service chaining. If you have a particular set of devices that are implementing some services, maybe a firewall, maybe some kind of cache, maybe some kind of load balancer, you might like to know that packets will traverse those services maybe in a particular order. And then there's other kinds of properties more having to do with performance, like load balancing. If you have a network that's supposed to be spreading incoming traffic flows over many possible paths, you might like to know that it's doing so correctly and it's not overwhelming some of the links because some devices are misconfigured. So what I'm going to do in this talk is tell you about two different projects that have built automated or mostly automated approaches for verifying the data plane behavior of networks. And I'll start with kind of a global view and tell you about a system called Netcat that we've been developing for about 3 years now. And here I'm going to focus on the ability to automatically prove network-wide properties. So we have a way to take a description of the entire network and check that it's doing something good. And then in the second part of the talk, I'll tell you about some more recent work where we're kind of drilling down and looking at just one device, but we're trying to verify that that device correctly implements a set of protocols that are specified again in software. Okay, so let me start with this first piece on network-wide verification in Netcat. So to set the stage, let me give you a little bit more detail on sort of why formal verification has started to be applied to networks. And this is sort of my conventional networking in one slide picture here. So if you take, say, an undergrad networking class at most universities, you'll learn about networks in terms of several different planes, in particular the control plane, which implements things like routing protocols, say BGP, OSPF, and so on. And the job of the control plane is to basically compute paths through the network usually by executing distributed protocols and exchanging messages between neighboring routers, and then doing some kind of path computation. And then below that, you have the data plane. And the job of the data plane is to actually forward packets. So you can think of it as the control plane is sort of computing some policy for the network, and then it communicates that to the data plane, and the data plane then implements that policy by using things like routing tables to process packets that are going through each device. So in traditional networks, these two pieces are usually sort of stuck together. So if you go buy, say, a router from a vendor like Cisco, they'll give you a box that has both of these pieces. And you can't really program it, and you can't really inspect its state except through, say, some kind of command line interface. And so the whole system is kind of closed. But a few years ago, people started to explore a different kind of architecture where these two pieces get separated. This is called software-defined networking. And the idea was to have somehow general-purpose programmable data plane devices, and then to move the control plane off from the devices, so do separate control, and maybe even allow one control node to manage lots of different data plane nodes. Say if you're in a data center, it doesn't really make sense to be always executing fully distributed algorithms. You can have a small number of machines that have a global view of the data center network, and then they just dictate the behavior of all the data plane devices. And so what's interesting about this picture from a verification perspective is now we have some kind of interface between the control plane and the data plane. And because these are really, residing on separate devices, there's now some kind of messages or some kind of programs that are running between these two nodes that we can start to inspect and then verify. So there are, I won't go into details today, but there are standard protocols that you can use to allow, say, a controller machine which is running a Java program or a C program or a Python program to directly configure the data plane behavior of a whole bunch of these programmable devices. And so by interposing something between these two pieces, we can start to do verification. So the model that I want you to think about is sort of a functional model. So I want to think of the network once the control plane has, say, computed a set of paths and configured the data plane. At this point, the network is going to behave like a big function on packets. So if a packet comes in at some ingress point to the network, it's going to execute some kind of function, and then eventually the packet will leave the network somewhere else or will possibly be dropped. And so the system that we've been working on is trying to come up with a sort of core language that captures an expressive set of these functional programs on packets. I won't pretend that this is how we came up with the idea, but if you sort of think about it from first principles, there's really sort of two things that a network does. One thing that it does is it classifies packets. So if you think about, say, a firewall or a router, the job of that kind of device is to sort of take all packets coming in, look at some of the values in the headers in those packets, and then decide to process the packet differently depending on the values of those headers. So that's a kind of classification that happens when you sort of take all the packets and decide how to put them into different bins. And then the second thing that a network does is it forwards packets along paths. And so here I showed the packet sort of taking this shortest path out to this destination, but you could imagine a network where you want packets to take different paths. And so the ability to be able to describe these paths in some convenient way is something that you want to be able to do. And so I'll just jump now to the language that we came up with for doing this. And again, this language did not we didn't discover this thing by first principles. It actually came by developing a number of much less pretty and much less simple languages. But it's basically what you get if you try to come up with a way to classify packets. And for that, we use standard predicates or elements of a Boolean algebra. And then you add to that the ability to forward packets along regular paths. So paths specified using regular expressions. And then you add a few primitives for manipulating packets as they're in flight. And you get this core language here. So I'll have some examples, but just to sort of show it to you piece by piece, at the top here you can see some standard familiar Boolean operators like true and false, and I'll call this operator here a test. Read that as test if field F of the packet that I'm currently processing matches the value n. And then I'll read this operator as disjunction, this operator as conjunction, and this operator as negation. So with those constructs, you can describe any sort of simple predicate on packets that you like. And we're going to throw into that the usual operators you're familiar with from regular expressions. So I'll think of this operator also playing the role of union, concatenation, and cleany star. And we'll be able to build up paths using the regular expressions, just like you do with ordinary strings. And then there's a couple of operators that I'll explain a little bit. One for modifying the value of a packet, and we use this both for rewriting header fields, if that's something that our device is going to do, and also for moving packets around in the network. We treat the location of the packet as just another header field that we can modify. And then we have one special primitive that we use to mark a path in the network growing by one more element, and we call that dupe. Okay, so this is our core language. And The name netcat comes from the fact that if you combine Boolean predicates and regular expressions, and you study the algebraic system that you get by sort of combining those two things, you get something called a Kleene algebra with tests, or a cat. And netcat is a particular cat where we have these additional packet primitives, and we interpret these programs as being functions on packets. This is a core language, but as I do examples, I'll use some syntactic sugar. So it'll be convenient, for example, to have standard conditionals and loops. And conditionals, if B, then P1, else P2, can just be understood by translation as the union of the concatenation of the predicate B concatenated with P1. So think of this as this filters incoming packets and retains only the ones that satisfy B, and then we run the true branch, union, filter the negation of B, and run the false branch. And similarly, we can encode a loop using just predicates again, iteration, and then negating the predicate to come out. I'll use this notation here, the third one, to encode links in the network topology. So one of the things that's a little bit unique about netcat is we don't just program the individual devices, we actually think about programming the whole network. And we view a link that connects two devices written, so if one device is named S and another device is S prime, this describes the link that forwards packets between S and S prime. We think of that just as a program that matches packets that are currently located at S. That's what this test says. Then we extend the path by one hop, and then moves the packets over to S prime, and then we extend the path again by one hop. So we'll use that to encode not just the behavior of the devices, but also of the switches. Okay, so that's the syntax of the language. And I'm not going to have a lot of programming examples in this talk, but you can trust me that you can write lots of interesting programs using just those operators. Semantically, I said that programs were going to describe functions on packets. And if we ignore this mysterious construct dupe, which I said extends the path that the packet's traversing by one hop, then we can actually interpret programs as functions from packets to packets. But if we add that operator back in, then we get a little bit more power, and we can actually describe programs that forward along different paths. So for example, we can distinguish the program that forwards on the top path, which I've shown here, from the program that forwards on the bottom path, because the type that I've written down here functions from what I'm calling packet histories to packet histories, where a history is just a list of packets. This gives us the ability to actually think about programming with these paths and distinguishing programs that might have the same sort of global input-output behavior, but use different paths to forward packets. Okay, so let me now jump in, sort of start developing some tools for encoding network configurations into this little formalism, and then some tools for actually solving verification problems. So the first thing I want to show you is that netcat's actually expressive enough to represent the kinds of data structures and programs that arise with conventional network devices. So for example, if you have a device and its behavior is captured by a routing table, where the routing table has sort of a list of patterns that sort of pick out sets of packets, and then actions that say how to process those packets, say by dropping them or forwarding them, we can use conditionals, which I just showed you, to build a netcat program that captures the behavior of that table. It's pretty straightforward. Likewise, if we have a network topology, here I've drawn a very simple topology with just 3 devices connected by links, I can encode those using the single link construct I showed you on the last slide. So this is a program that just captures all the forwarding that happens on these links. And now, if I have these 2 programs, I have the program that captures the routing tables on all of my devices, and I have the program that captures the behavior of all the links in my topology, then I can use the Kleene star operator to build a program that captures all the processing that this network could do from input to output. In particular, it's just all steps of processing that happen when I run the program on the devices and then run the program on the topology and do that arbitrarily many times. If you think about a packet going through the network, it's going to go device, topology, device, topology, device, topology. So that's what this term captures. And so we can use this to actually model the sort of end-to-end behavior of the network as a kind of program. Okay, now that we have this way to model networks as programs, we can start to think about doing all kinds of program analysis or verification on those programs. And normally, if you have a programming language that's expressive enough to capture the interesting programs in your domain, it's usually a Turing-complete language, and so things like Rice's theorem tell you that you can't actually decide non-trivial properties of that language. In the case of Netcat, the language is very much not Turing-complete, and so we're actually able to decide whether two arbitrary programs are equivalent. And that comes from the fact that there are only a finite number of possible packets, and our programs are stateless. And so we don't actually suffer from the sort of curse of Turing completeness and Rice's theorem and so on. And in particular, there's actually a way to translate Netcat programs into equivalent automata representations, and finite state automata. And so we can use that to come up with a way to decide when two programs are equivalent. And as I'll show you in a few slides, we'll be able to take interesting verification questions that we have and encode those as equivalence questions, and then use this technique to actually answer those questions. So the kind of workhorse of this verification tool is going to go by taking our programs, turning them into automata, and then checking if those automata are equivalent using standard techniques that you learn in an undergrad theory of computation course. So let me tell you a little bit about how you turn programs, Netcat programs, into automata. The details are a little bit involved because our programs actually, they're these sort of functional programs that describe how to process packets. And the way that this works is based on an idea that some of you may have seen called finite state derivatives. So how many of you have seen derivatives before? Oh, less than I thought. Okay, so if you remember back to your theory of computation class when you studied formal languages, you may have seen the definition of a derivative. That's what's shown in the blue box here. So the derivative of a language L with respect to a character is just all the words that are left after chopping off that character from some string in the language. So it's kind of the residue that's left after finding strings that start with that character. So if you have a way to calculate these derivatives, then there's a very elegant technique for building automata due to Bruszowski, where we basically label the states of our automata with the programs or regular expressions, and then we go compute all the possible derivatives. And if we're working with a finite alphabet, then there's a finite set of those possible derivatives. And that gives us a residual language, which it turns out is also regular. And we can just continue this process until we don't have any more regular expressions to consider, and we have a finite state automaton. And the only thing left is to decide which states are final, and we label a state as being final if it contains the empty string, which you can also easily decide for regular languages. And it turns out that these derivatives can actually be characterized syntactically. So here I gave a semantic definition just in terms of sets of strings, but you can come up with a simple syntactic translation on regular expressions that gives you a regular expression describing the derivative. Moreover, every program has a finite number of distinct derivatives up to a fairly simple equivalence relation. And so you can actually effectively do this and build deterministic automata directly from expressions, sort of using this idea of derivatives. So that's a review of kind of how this works in the simple formal language case. In the case of Netcat, things are a little bit more complicated because we think of these programs as being functions on packets. But actually, there's an equivalent sort of formal language view of what a Netcat program is. And that is that they recognize these sort of funny strings that always have a packet at the beginning and a packet at the end. And then in the middle, they have a sequence of packets separated by dupes. So the idea is that obviously the input and output capture the first and last packet in our history, in the trace that the packet takes as it goes through the network. And then the intermediate packets are all of the values of the packet as it's in the middle of the network. And so we can build finite state automata that recognize these kinds of strings. And it's almost like a standard automaton. So there's a finite set of states, an initial state. But instead of an acceptance state, we have an acceptance function. So sort of when we reach the end, we don't have the empty string. Our smallest strings are pairs of input and output packets. And so we have actually a function that in a given state tells us for a given input packet which output packets will be produced. And likewise, when we transition, we don't just sort of consume a character. We actually sort of take the current packet, produce a set of output packets, and transition those packets to some new states. So it's sort of like regular automata, but you sort of replace every character with functions from packets to packets. And it turns out that just like in the case of regular expressions, we can define syntactic notions of derivatives for netcat programs that exactly correspond to that notion of acceptance and transition. So I won't pronounce everything on this slide because it's pretty complicated, but essentially that acceptance function that I showed you, we can calculate that syntactically by this function E. And the way to think about E is it gives us a representation of the function on packets that we get when there are no hops left. So in particular, you see that the case for this dupe construct that produces always extends the hop by 1, that's the false program that does nothing. But the other programs, they do produce sort of interesting functions on packets. And the way we represent those functions on packets is, again, as netcat programs. So this is just a recursive function that takes a netcat program, gives us another netcat program, but it gives us the netcat program that captures just that local behavior when there's no more hops in the history that we're processing or recognizing. In the same vein, we can write down a syntactic definition of the transition function of this automaton. This is given by this function D. The way to think about D is it gives us a representation of the processing that happens up to the next hop, which is marked by this dupe operator, and then the state of the automaton that we get to, and then the rest of the program or the continuation that follows. And so the way this is formalized is that this D function gives us actually a triple with a local program that describes the processing up to the next hop, a label which corresponds to a particular occurrence of dupe, and you can think of this label as capturing one state of the automaton, and then another netcat program that captures the continuation after we go to that state. And again, I won't pronounce this for you. If those of you who have seen derivatives, you can kind of check that this looks similar to what you might have seen for regular expressions, but you can trust me that this definition captures that semantic notion. And now, once we have these two translations, we can go build automata as follows. We take the set of states to be basically the set of dupes that occur in our program. So there'll be one state for every syntactic occurrence of dupe, plus one fresh state, let's call it 0, that stands for the start state. And then this E function on our programs exactly corresponds to the acceptance function for our automaton. So given a state L and a packet PKT, the way the acceptance function works is we go find the continuation of the dupe corresponding to that state, and you can prove a theorem showing there's a unique continuation, and then we take the E function of that, and that captures the acceptance condition. And similarly for the transition function. So from a given state, given input packet, we go find the transition from the continuation of that state, and then go evaluate the function from there. Okay, so that's the most technical part of this talk, but that tells us how we can go from programs into equivalent finite state automata. And now that we have these automata, as I said before, we can now check them for equivalence using a standard bisimulation algorithm, or if you want, standard graph isomorphism. And so now I'm going to show you how we can take some of the kinds of properties that I started out with as motivation and reduce these to equivalence. So the whole idea is going to be that we have some network. It's configured, maybe using some conventional tools, and we encode it into netcat, as I showed you, and then we're going to ask if it satisfies some property. And we'll do that by producing an equivalence question that we can then use our decision procedure to answer. So for example, if we want to know, does the network isolate A and B, where A and B are two endpoints, and we can capture A and B as predicates in netcat, then we can turn that into an equivalence question by taking our model of the network, our program for the switches, our program for the topology, iterated, and then we just surround that with the predicates for A and B. And so basically this program on the left captures everything the network does, starting from A and going to B. So if there is some path that gets from A to B, then this program will not be equivalent to false. But if there is no path, then it will be equivalent to false. And so we can check that isolation condition by just checking this equivalence here. And we have to check the other direction also with B and A inverted. So that's kind of neat. And there's lots of other reachability questions, including things like service chaining. Does all traffic traverse a specified set of waypoints that you can encode in similar fashion? It's just a little bit more complicated, but very similar constructions. Let me show you one other application of this automata representation that turns out to have a kind of slick solution in netcat. So you may remember I talked about forwarding loops, and I said these were really bad because when you have a forwarding loop, so there's some packet that can come into your network and get to a location and then take some non-trivial path and get back to that exact same location with the exact same value. If your network's deterministic, then the packet is just going to keep looping around forever. Or at least until, if you know about things like IPTTLs, eventually the packet will be, its time to live will hit zero and will be dropped, but you'll still have a lot of wasted resources as this packet cycles around and around and around. So we'd like to be able to check these kinds of properties in netcat. And intuitively, if I just sort of grant myself a little bit of hand-wavy notation, what I'd like to do is, for all packet values, let me just use the character alpha to range over a predicate that captures an arbitrary packet value. I'd like to know, is there a way to go through my network some non-empty set of steps? So this is like the normal plus operator that desugars into clean E star composed with the thing inside again. So can I get to alpha? And then can I go through the network again and get back to alpha? So if this is false for all alphas, then there's no loops. So the question is, how do I answer this question somehow efficiently? And it turns out that using our local semantics, where we ignore the behavior of dupe, so we just look at sort of input-output behavior of the network, and this automata representation, we can come up with a very efficient way to check this loop freedom property. And the way this works is we first compute that E function, which gives us the acceptance condition for our network, on this program. So just the model of the network. Here I've restricted it to an ingress, but in general the model of the network. And then I go find all packets that do not get dropped by that program. And in general, this, most packets are actually dropped. And so this will be a small set of the total set of packets, and I can check this symbolically. I can find symbolic ways to represent the sets of packets that are all treated the same. And then for each of those packets that sort of go through the networks partially, I then check if, again, if they can get back to themselves. And so the key thing here is that I'm using the automata representations to quickly answer this more complicated property that involves a quantifier. And if you use the fact that, again, most network programs are relatively simple, you can actually have a sparse representation of this E function as a kind of matrix, and you can represent sets of packets symbolically, and this whole question can be answered quite efficiently, and it scales up to real-world networks with thousands of switches and realistic configurations on those things. Okay, so that gives you a taste of how you can use this finite state domain-specific language that's still expressive enough to represent sort of interesting programs to do practical verification. So I think I have about 10 minutes left. Is that about right? So now I want to shift to the second part of the talk and say a bit about something lower level, which is how we can verify properties of single devices. Question? Yeah. I want to check this, but this is done sort of outside of the decision procedure. And same for here. Here I'm basically iterating through elements of the representation of the acceptance function that are non-zero. Yeah, the decision procedure only decides for concrete programs. Okay, so I started out by giving you this kind of cartoon version of what software-defined networking is about. And there's something that is cartoon and a little bit silly about that. And that is that actually, if you want to program your network, you actually want to do more than just configure these kind of stateless routing tables. And some of the early proposals for software-defined networking standards didn't actually expose to you very much control over the data plane behavior itself. And so about 4 years ago, a group of engineers at Texas Instruments and some researchers at Stanford kind of got together and said, what would happen if we just tried to make a generic programmable data plane device? What would that look like? And they came up with this architecture that you see down here, which I'll explain in a second, that kind of gives you the flexibility to really define the behavior of one of these data planes without sacrificing performance. And at the same time, as they were designing this architecture, they also started to think about programming, and they came up with a little domain-specific language called P4 that lets you program this kind of architecture in a fairly clean way. So let me tell you a little bit about kind of how packets kind of flow through this architecture, and then we'll see how they flow through the program in the next few slides. Essentially, a packet comes in, and the first thing that we do to the packet is to parse it. So the packet is sort of just an unstructured set of bits. But if we're going to modify it programmatically, we want to be able to access it in terms of types and use kind of structured control flow programming over it. And so the first thing we do is we run the packet through a parser, and we get somehow a parsed representation. Think of this as maybe a struct in C. So now we have a bunch of bits from the packet that we've sort of picked out, and now we can process. And then we have a couple of pipelines, an ingress pipeline and an egress pipeline. And as packets flow through those pipelines, we have a limited set of operations we can do to those packets. So we can classify them using routing tables. We have some arithmetic units we can use to do simple computations on the packets. We might add and remove data, as I'm showing here. And so the packet's going to kind of flow through and be modified piece by piece. In the middle, we have something called the traffic manager, which does things like schedule the packet, does queuing and so on. And then on the egress side, we have the ability to do additional processing. And then finally, at the end, we actually unparse the packet and put it back into a sequence of bits that we can send out on the wire. So this is this architecture, which is called RMT, and there's a language called P4 you can use to program devices that implement this architecture. So the main thing in this P4 language is that they wanted it to be efficient. And so the kind of slogan you can think of is that you should do a constant amount of work in a constant amount of time. And that leads you to certain kinds of language design choices, such as not having pointers, not having complex data types. The memory model is very simple. All the state is bounded. There's no loops. And so it's a very simple language. The main construct that's sort of interesting and different than languages you might be familiar with, is this thing called a match action table. And the idea with a match action table is it's much like the routing tables we saw before, but now, because the very format of the packet is something we can program, we have to specify what state of the program should be fed into this table in order to do matching and how we should do matching. And then we specify a set of procedures that can be applied to packets that match entries in this table. So here's one of those procedures drawn from an Ethernet learning example. So this is what you write in your program. Of course, when you actually run this thing, the table needs to have some values, and those are populated by the control plane, which is not part of this program. So all of the specific values of addresses and the specific actions that should be applied to packets that match those values, that's not something that our program specifies. Let me just give you a kind of macro picture of what one of these programs look like. So this is a simple program that implements an Ethernet switch. And what it consists of is a bunch of type definitions for things like the bits that go into the Ethernet header. It has the packet parsers, which say how to go from a sequence of bits into those more structured representations. It then defines a set of actions, all the different modifications you might make to packets in a switch. Then it has a sequence of tables. And then there's this last piece called the controls, which is basically sort of the main function that says which tables you should apply and in what order. Okay, so this is a small program, but it kind of shows you the main elements of P4. So one of the interesting things about this language is by sort of opening up the guts of a switch and making it more programmable, you increase flexibility, and that's, I think, a good thing. It lets you customize switches with new features. It lets you take out features you're not using, maybe optimize your switch to use resources in a better way. But it also opens up a whole bunch of possibilities for new kinds of errors. So for example, P4 is not a safe language. Some of these types have unsafe operations on them. In particular, the type that represents packet headers has a notion of validity. And if you ever read or write an invalid header, then you get an undefined value. And then your program might behave in crazy ways. And then all the kind of standard issues that arise in low-level languages like, do you handle exceptions? There's various metadata that exists on the switch. Are you using that correctly? How do you actually direct the switch to clone or forward a packet? You can produce malformed packets. And your program might have specific control flows that are standard kind of program properties that you want. But you can write your program in a dumb way that doesn't have those properties. And so one of the things I did last year when I was working at Barefoot Networks on sabbatical was we developed a fairly standard program verifier based on sort of Hoare logic and predicate transformers that works much like a lot of the tools that we've seen developed over the last 20 years. We take P4 programs, we desugar them into guarded commands, we then use a VC generator to produce a first-order formula that captures the preconditions for that program, and then we ship it off to an SMT solver and either get find that our program is correct or get a counterexample. Let me show you a couple examples just of the kinds of things you can do with this kind of tool. Can I defer questions to the end if that's okay? I'm a little short on time. So I mentioned this issue with header validity. And so in particular, the type that represents headers, they can be either valid or not. And if your program ever accesses or modifies an invalid header, then you get an undefined value. But actually, the structure of packets is really complicated. So this is kind of a zoomed-in picture of the parser for a big program that implements the functionality you'd find on a standard router. And you see sort of all these different control flows through the parser. And each path through this parser corresponds to a set of header values that will be simultaneously valid. So you can see that not all packets have MPLS, not all packets have IPv6, not all packets have IPv4. But your program has state for all those headers. And so as you're later on writing tables that end up processing those headers, you can very easily end up with a control flow through your program where you end up accessing a header that isn't valid at that point. And P4's type system doesn't give you very good tools for checking this. I was going to do a demo, but I'm long-winded, so I'm out of time. So let me skip the demo and offer, if anyone wants to see a demo, I would love to do one during the coffee break or anytime today or tomorrow. And let me jump just to one more example of a more interesting kind of property that you might want to check in P4. So this is an example of that's actually drawn from that big program whose parser I just showed you. And it's a little bit of a silly program, but what it's trying to do is it's trying to decapsulate all packets kind of at the last hop before they are on the wire. So as packets go through the network, they may have a number of tunneled protocols that get stacked up against each other. And this final table is supposed to strip off all layers of encapsulation and just give you the raw packet. And so what we'd like is the ability to say, when this program finishes running, it's not the case that there's any encapsulated data. All the layers from encapsulation have been stripped off. And unfortunately, the challenge is that the way this is done for sort of silly reasons having to do with how resources are allocated on devices is actually using a table. So this table is matching on the validity bits of up to 2 layers of encapsulation and then applying one of 3 actions depending on the combinations of bits you have here. And the problem is, there's nothing to stop you from matching an already fully decapsulated packet and then applying this procedure remove double tagged, which is going to manipulate some invalid headers and produce a mangled packet value. And the way I would say this pictorially is that a P4 program is really only half a program. It only really describes the structure of the tables, but it doesn't tell you what the control plane is going to do. And so if we want to build an effective verification tool, we need a way to somehow document assumptions about the missing part of the program. And this is my last technical slide. The way we do this is using a standard technique, just instrumenting the program with ghost state. So what our verifier does is it sort of introduces this extra piece of state, and then it instruments all of the procedures and all of the tables so that we can track which tables and which actions were applied. And now we can start to formulate assumptions about how the control plane works, like certain tables must hit, or those tables must hit and apply this action on particular kinds of values. So again, I'd be happy to show people a demo of this. I'm wholly out of time, so I won't do that now. But what we found in practice is that this domain of, even though these programs are kind of large, they grow to be kind of tens of thousands of lines of code, because everything is so restricted, you can actually do quite a good job with mostly automated techniques. Z3 is super fast, and you can take real-world industrial programs and real properties and throw them through the tool, and it pretty much instantaneously solves them for you. Okay, so just to wrap up, the intersection between formal methods and networking has gotten very interesting in recent years. You see these real drivers from industry where there are startups, and also the big companies are starting to develop tools and verification teams to examine the software running in their networks. And then also, I think the emergence of these software-defined networking platforms and languages like P4, they're kind of a unique opportunity that our community can sort of have impact on a more applied community. Because I think a lot of these abstractions are sort of getting laid down, and if they're successful, they may actually be used for several decades. So there's kind of a unique chance to get things right. There's lots of challenging problems. Of course, doing network-wide stateful verification is an important problem, and some people in the room here have worked on that. There's quantitative properties. If you want to talk about things like load balancing or probabilistic behavior, that's a very interesting space to work in. And then another place that I think is super important is the tools that we might build are ultimately going to be used by people who are not programming language or formal methods people. They're not even necessarily programmers. They might be these network engineers. And so finding ways to make these formal methods usable by non-experts is really critical. All right, so I'm out of time. Let me stop there and maybe take a question or two and then defer the rest till after coffee.
Yeah, let's thank Nate. Questions? Somebody had a question. Okay. So I guess you were there during the talk. Who had a question during? Yeah.
Very simple question: whether the properties of these P4 programs that you're trying to verify are sort of program specific or general to all P4 programs. And it sounds like at least some of the properties are general. Like you can say for any program, it shouldn't access a non-existent header field, but some of them can also be program specific.
That's right. So our front end supports basically adding assertions and assumptions for kind of stock safety properties, so that non-experts don't have to write those things down. But of course, if you want to know that this table is applied and then this table is applied, you need to write down something, annotate the program in some way.
Yeah. So you mentioned actually on this slide that you use go state to connect the control plane to the data plane. This slide, exactly. So do you have a formal story? I mean, what if you make a mistake there with your assumed statements? Would that lead to unsound reasoning, or is there some kind of connection how you insert this go state?
Yeah, so yes, you can lead to unsound reasoning. You can assume false about the control plane, and then the verifier will always succeed. We haven't built this yet, but eventually we will actually instrument the control plane with a runtime monitor so that at least dynamically we're checking those assumptions.
Any other question?
So in the netcat approach, so in this the system basically, I mean, the netcat program, it would capture a particular data plane. So I was wondering, what is exactly the use case? Because the data plane is quite dynamic, and the program doesn't capture anything about the control plane, basically. So would the controller, for example, check the properties upon any message?
Yeah, I should have made this a little bit clearer. So there's a bunch of tools that really do interpose right here. So every time the controller makes a change to any data plane state, they go run a verification tool. So there's tools like Veriflow, and there's a startup now based around Veriflow, and something called header space analysis. They work this way. Of course, if you're willing to go examine the software running up here, it'd be much better to do more static verification and check the control plane. Make sure the control plane never generates a bogus data plane. And there's also work on that. Actually, Todd Milstein, who's from our community, has worked on that. And there's, with Ratul Mahajan and Dave Walker, there's actually a startup looking at that problem as well. That problem is more difficult for several reasons. One is that, of course, this is much more like a general purpose program. So you're really kind of doing general software verification at that point. You also have to worry about the fact that the network is a distributed system. So if you have multiple control planes, you may have to worry about, the property, like how the distributed protocol executing between those control planes is working. And then there's the kind of practical problem that these control planes are implemented by lots of different vendors. And so you kind of have this last mile problem of how do you kind of get there, how do you extend your tool to work with all these different kinds of control planes. And that's sort of just an engineering problem that some of the startups have just been solving by basically building lots of adapters that can suck in configurations from lots of different control planes. Yeah, that's a promising area, and the problems sort of get another dimension harder.
Can you comment on some analysis questions that you cannot capture in netcat? At the end, you talked about quantitative properties. Would that be one example?
Yeah, so netcat is very much based on this stateless model. So anything that involves properties of two packets is just out, or anything that involves a piece of state on the switch, like think of some kind of register that can be read and written, which exists. Languages like before expose that to you. In netcat, you just can't talk about that.
So initially, we're also in your introduction talking about fault tolerance or misbehavior. Is there any way you can express things like that in netcat other than just coding them up directly?
Yeah, so I guess there's two stories or two answers I can give you. So one is we worked on a version of a language just before netcat where we actually added fault tolerance annotations to programs. So you could say, here's this program, it describes a set of paths or a function from histories to histories. Make sure that it's at least k-fault tolerant. And what the compiler did is it then took that program and it made sure to lay down enough backup paths along with the logic to switch from a primary path to a backup path depending on local failures. So that's one way you can sort of take netcat and sort of make it by construction fault tolerant. The other piece of work that we've done that falls into that is if you add something like random choice to the language, you can start to encode links or sets of links that fail with some probability. And then you can start to analyze the probability that packets will be delivered given that devices or links might might just crash with some probability.
Okay, so I think let's thank Nate again and take the rest of the questions offline.